In this video, we're going to go into greater depth about the Cauchy-Riemann equations. In particular, we're going to show that if a function satisfies the Cauchy-Riemann equations and is C1, then it is automatically analytic. We'll then go into a little more geometric interpretation of the Cauchy-Riemann equations and show that analytic functions are locally conformal, which means that they're locally angle preserving. And after that, we'll get into some applications to harmonic functions. The first thing we're going to do is see how differentiable functions compare to complex differentiable functions. So let's start working in R2. So let U be an open subset of the plane, and let G be a function on U mapping into R2. So this will all be real value stuff. And you recall that G is differentiable at a point U, Z0, if you have a linear approximation to G at Z0, meaning G of Z minus G of Z0 minus this linear term. So here B is a real 2 by 2 matrix. If this linear approximation to G is much smaller than a linear term, so is little o of Z minus Z0, then usually in a real analysis course or multivariable calculus class, you would show that then this matrix B is uniquely determined and is equal to the matrix of partial derivatives, so dg1 dx, g1 dy, g2 dx, g2 dy, and this is the derivative matrix of G at Z0. So this is differentiable. Now let's compare this to complex differentiable. So recall that f on U mapping into the complex plane now is complex differentiable at Z0 if we have this linear approximation, but now it's a complex linearity, so I use a complex number and complex multiplication if this linear approximation is little o of the difference. Now let's convert this to real variable language. So we'll think of we'll write out the real and imaginary parts of f, but now we'll convert f to a vector, and we'll convert z to a vector xy, and let's write out the real and imaginary parts of the derivative at Z0, and we'll do something that we did in the very first lecture, which was if I convert everything to vectors in R2, then this multiplication here becomes multiplication by this type of matrix. And so we get something that looks exactly like differentiability, except our derivative matrix has a very special form. It's a matrix that, when it's not zero, is actually a conformal matrix, which means it preserves angles. We also talked about in the first lecture how you could go the other way. So if you have a vector equation like this, and you have a matrix multiplication using a matrix of this form, well, it converts back into a complex formula where you have complex multiplication right here. Because of this, we can convert between complex differentiability and differentiability with a derivative matrix with a certain form. So that's just what I'm saying here is, if I have f complex differentiable at a point Z0, then f will be differentiable at that point, and its derivative matrix will have this form, AA minus BB. And as I just said, you can then convert this back to being complex differentiable at Z0 by turning our vector equation into a complex equation. But what does it mean to have your derivative matrix of this specific form? Well, it exactly means the Cauchy-Riemann equations are satisfied, because I have the partial of f1 with respect to x equal to the partial of f2 with respect to y, and similarly you analyze the off-diagonal elements to give you the other half of the Cauchy-Riemann equations. So the Cauchy-Riemann equations are equivalent to the derivative matrix having this particular form. So out of all of this and some observations from the first lecture, we get the converse of something we've already shown. So we assume f, here written now as u plus iv, defined on an open set mapping into the complex numbers, assuming that it's C1, so differentiable with continuous first partials. Then f is holomorphic or analytic if and only if the Cauchy-Riemann equations hold. And we've already proven this from our observations. So as we've proven in a homework exercise, matrices of this form, at least when they're non-zero, act as angle-preserving linear transformations, and so analytic functions are going to be locally conformal, and we'll show some pictures of this on the next slide. Okay, so again, if I have a holomorphic function, then when we vectorize it and take its derivative matrix, this will be either a conformal matrix or the zero matrix. And one thing this shows is the partial derivative of the vector with respect to x, which would be when you apply 1, 0 to our derivative matrix, this will be orthogonal to the partial of f with respect to y. And so this would be a tangent vector that you get by viewing the curve you obtain by letting x vary and keeping y fixed, whereas df dy will give you a tangent vector obtained by letting y vary and have x fixed. And here are some examples of this phenomenon. Let's look at the map z goes to z squared. So here I have drawn what the map z goes to z squared does to a bunch of horizontal and vertical lines. And you can see that obviously horizontal and vertical lines will be orthogonal to each other, and they map to curves that have tangent vectors that are orthogonal to each other. For another pretty picture of this, here's what z maps to z cubed does. You do have this square here being kind of wrapped around itself, so you get points mapping to the same point multiple times, but locally the same phenomenon is still happening. So I have, for instance, this curve orthogonal to this one, and this curve orthogonal to this one. You can also view this through the lens of level curves. So if I have an analytic function written as u plus iv, then the different level curves of the real and imaginary part will be orthogonal, meaning their tangent vectors will be orthogonal at points of intersection. So why is that? Well, the gradient of u is going to be orthogonal to its level curve, and the gradient of v will be orthogonal to its level curve, but then you can just use the Cauchy-Riemann equations to show that ux, uy is orthogonal to minus uy, ux. And note out of this that since there are only two dimensions here, the gradient of v will actually be tangent to the different level curves of u, and the gradient of u will be tangent to the different level curves of v. And here we can see, or we've drawn level curves of z squared, that they are indeed tangent to each other, or sorry, orthogonal to each other. And the same thing happens with z cubed. You get this nice picture. So all the different level curves of u and v will be orthogonal to each other. Next, let's talk about some applications to harmonic functions.